So before we start talking about precipitation reactions and acid-base reactions, we actually need to understand some basics about how ionic solids dissolve in water. So ionic solids, essentially the main idea from this is they love to dissolve in water. Like as soon as they get in water, both the cation and the anions, they love interacting with the water molecules that end up surrounding them. So you can see here, for example, we have sodium chloride, right? The sodiums are the purples, and then the chlorides are the greens. Um, Essentially, the water molecules will like give them a hug. They all join and give them like this giant group hug to both sodiums, cations, and the chloride anions. So that's the main idea from this. Ionic solids love to dissolve in water. So whenever we have ionic solids dissolved in water, we actually call them electrolytes because they can actually conduct electricity. So here we have an ionic solid dissolved, in other words, a salt, and then here we have sugar. Sugar is not an ionic compound, so it will not generate electricity when dissolved in water. So that's a non-electrolyte. So electrolyte versus non-electrolyte, ionic versus non-ionic compound, essentially. I'm pretty sure y'all heard my cat just meowing. Anyway, ignore that. So just to give you a visual on how molecular compounds dissolve compared to those ionic compounds that we just looked at, essentially these, yeah, they'll interact with the water, but you can see that the water isn't like hugging them the way that it does for ionic cations and anions. So you can see that those interactions are a lot less in comparison to ionic compounds. So we can further categorize electrolytes. So we talked about non-electrolytes versus just electrolytes in general. So of the electrolytes, we have strong and weak electrolytes. Strong electrolytes will completely dissolve like 100% into ions, so dissociate 100%. And those are our ionic compounds and our strong acids. Weak electrolytes will mostly be molecules, but partially you can find them as ions. And these are our weak acids that will be weak electrolytes. An example here is acetic acid. So this is a acetate polyatomic ion, and this is its like acid version that we're starting with right there. So it's a weak acid, so it doesn't completely go to being hydrogen ions and acetate, but it does partially. So you have several different terms about how ionic compounds dissolve versus what happens with acids in water. So when ionic compounds dissolve in water, the ions are dissociated from each other. So they are just like pulled apart from each other. So you can see that here. Whenever you have ionic compounds that have polyatomic ions like this, the polyatomic ions will dissociate from the cation, for example. Here, this is a polyatomic anion, but the polyatomic ion itself will stay intact. So please keep that in mind, that it'll stay together as one ion. Ionization refers to whenever we have strong acids that dissolve into water. This originally was like theoretically like a molecular compound, but it ionized, so it turned into H ions, H plus ions, and it's whatever anion it has. So I said ionic compounds love to dissolve in water. Is that true all the time? No. So there's a degree of solubility that ionic compounds can have. Many ionic compounds love to dissolve in water, but there are a few that do not like to do that. So an example is sodium chloride. And whenever we have compounds that love to dissolve in water, we call them soluble. And when they don't like to dissolve in water, we call them insoluble. So here's an example of how it would look like when you put it in water. It's just going to stay as a solid as it is. And again, here we have another ionic compound just completely dissociating. So you're probably wondering, okay, so how do I tell when an ionic compound is going to want to dissolve? So that has to do with something called solubility rules. Now, solubility rules are an empirical method. What an empirical method means is these observations have been made, and then we're taking these observations that were made, and we are making them kind of like into this rule. So that's where all of these rules come from, and we're going to learn how to use these solubility rules. So we are talking about these solubility rules because we are trying to get to these precipitation reactions. So we're trying to learn about these, but I needed to introduce those things first, about the solubility rules, about dissociation. So a precipitation reaction is whenever you have two dissolved substances, so usually it's two ionic compounds that are dissociated in water, reacting to form one or more solid products. An example of this that happens very often to people are kidney stones. So your kidney stones, whenever they form, it's because it's a precipitation reaction occurring. So when your urine contains high concentrations of calcium and oxalate, oxalate will actually, like you'll have high concentrations of oxalate whenever you consume a lot of high fructose corn syrup. So high fructose corn syrup is in many like drinks, sugary drinks, in a lot of like fried food, sugary stuff. They'll add it to that, and it'll increase your oxalate in your urine. And then also phosphate. So whenever you drink a lot of soda, it has a lot of phosphoric acid, so that'll increase phosphate in your urine and your circular that system, whatever it's called. But essentially, whenever you have all of these combined, what it does is it helps like increase that formation of the kidney stones. So here, what you see right there, that's an ion. It's actually the oxalate. I know it's not part of the polyatomic ions that we learned, but it's a polyatomic ion. So you have a lot of this, right? And then you also have a lot of calcium from all of those drinks and everything else. When you have high amounts of those in your system, it causes an increase in calcium oxalate, which is what your kidney stones are made of. So you can see here it's a solid, so that's what makes up those stones. So here you can see this is our potassium iodide, which is soluble, and our lead nitrate, also soluble. When we mix it, what we get is an insoluble solid right there. I just said the same thing. But essentially you can see the precipitation reaction occurring like as you pour it. It's immediately those ions are gonna find each other, the lead and the iodide, and they're gonna form together to form a solid. So something to point out before we go further is whenever you have two ionic compounds that are both soluble, and when you find out what the products are and you find that both of those are also both soluble, like nothing is insoluble, nothing forms a solid, essentially what happens is you don't have any reaction. So if you have no precipitation, so if you have no solid form, you had no reaction occur between these two ionic compounds that were dissolved in water. So again, like many problems that we have to do in chemistry, there is like a set of guidelines that you can follow, and that'll be like your recipe for solving. So for predicting precipitation reactions, we have to determine what ions each reactant has in the first place. So you have to essentially split the ions up. So that's what you would do first. Secondly, once you split these up, you are able to exchange the ion. So essentially you treat both reactants, you treat them as pairs of like partners, so like life partners. And what we end up doing actually is they end up switching partners for the products. So that's what we mean by exchanging ions. So we're going to practice this like in a second, so don't worry. From there, we will balance the charges in order to get the actual finished like formula, nice and balanced and neutral. From there, that is whenever the solubility rules come into play. So after step 2 is when you would pull out your solubility rules, this table right here, and that's whenever you would check whether your products are soluble or not. Most of the time, the reactants I'll give you will be soluble, so obviously you don't have to worry about checking the reactants, but check the products. If a product is insoluble, so that means it will form a solid, so you will have to write the state as S, then it will be considered a precipitate. If none of your products form a precipitate, that means you have no reaction. So just like we saw previously on that slide where we had two reactants that don't produce a product, that means you don't have a reaction. And I kind of mentioned this already, but for whenever you have a precipitate form, you would indicate that it's a solid by writing what the state is. And then if something is soluble, you would say that is aqueous, so it's still dissociated into its ions in the water. And then finally, you would balance the equation. So just a reminder, don't change the subscripts, you're only changing coefficients. There are several different types of equations that we can refer to when we're talking about precipitate reactions, acid-base reactions, and just ionic equations in general. And the first one is the molecular equation. This is just the regular equation that we've been learning about where we have our reactants and our products. Everything has a state, everything has a coefficient if necessary. It's just a regular old equation. Now this is new. This will be new to you. This is called the complete, it can also be called the total complete ionic equation. In this equation, we will state explicitly whether they are ions or not. So here are some rules for that. So aqueous strong electrolytes, such as soluble salts, strong acids, strong bases, these will be written in their ion form. So for example, KOH, right? This is an ionic compound that is soluble. Like when you check the rules, you'll see that it's soluble, and obviously it says aqueous, so you know that also tells you it's soluble. What you have to do is you split it up into its ions. Now because it has a coefficient, you have to place that coefficient in front of everything. So here you have potassium and hydroxide, they both have that too, so it applies to both. And remember to write out the charge. And you can kind of see the same pattern for everything else. Now anything that's insoluble, any weak electrolytes or non-electrolytes, will be written in their molecule form. And I don't like this term molecule form, I mean like just in their regular form. If they're an ionic compound, you write it in that way. So an example of that is our magnesium hydroxide here. Everything else was soluble, right? All of these things, they're all soluble, aqueous, and written in their ionic form. This, it had a solid after it, right? Whenever it has a solid, a liquid, a gas, that means you will not break it up. For the most part, for these precipitation reactions, you'll see solid. When you see that solid, do not split the equation up. You'll just bring it down the way it was written. So some more terms that you need to learn are about spectator ions and net ionic equation, what that is. So spectator ions are ions that do not participate in the reaction. So they're spectators, like how whenever you go watch a football game, a basketball game, a baseball game, you're a spectator in the audience, right? And the people playing, so the people that are reacting, are the ones that are considered like part of the reaction. So in order for you to be able to recognize where the spectator ions are, all you have to do is look at the ones that do not change on either side. So they'll stay exactly the same on both the reactants and product side. So here, for example, we have this nitrate and this potassium ions. You have two of each, and then you find that at the end, you have those same ions, and nothing really changed. They stayed aqueous. There's still both two of them of each. That's pretty much, they didn't do anything, they just stayed the same. So they're spectator ions. And then whenever you want to write your net ionic equation, you have to have already identified your spectator ions. So net ionic equation will be the complete ionic equation, but all you do is you cancel out the spectator ions. So here what we did, or what I did, was I canceled out that potassium, that nitrate, and again on both sides, right? And then what we get is this nice, neat little equation that doesn't have those spectator ions that didn't do anything. And you have what actually participated in the reaction. And it's much easier to use and just to see what actually happened in the reaction. So here I gave you a molecular equation, right? And I want you to write out an ionic and a net ionic equation. So what I mean is like the complete ionic and then the net. So you're going to follow these general guidelines. You're going to dissociate the ions. It'll give you the complete ionic, and then we'll identify the spectator ions, cross them out, and then that'll give us the net. So let's go ahead and get started. So I'm going to split everything up. So remember, you have to consider how these actually look in solution. So whenever this breaks up, what you end up getting is 2 potassiums and just 1 sulfate. Because this subscript only applies to that potassium, that's just remember that it's not a coefficient, and this is a coefficient, so it will apply to 2. It will apply that 2 to both of these things. So let's go ahead and get started. So I have 2 potassium. These are aqueous, right? Because that's what that says. Next we have 1 sulfate. Sulfate has a 2- charge, so break out that polyatomic ion chart if you don't know the charges. And then we have this coefficient in front of this silver nitrate. Silver has a +1 charge, aqueous. And then again, that 2 is a coefficient, so it applies to the nitrate as well. Remember, nitrate's charge is -1. So that's our reactants. Now we're going to write out our products. So this applies to everything. This only applies to this right here. And this is sulfate, so that 4 is part of the polyatomic ion. Or, oh, actually, I'm getting ahead of myself. This is a solid. You don't break this up. So just ignore everything I just said about that one. But this aqueous one, we do break it up. So 2K plus aqueous plus our 2 nitrate, aqueous. And then we have our solid. So we're not going to break that one up. It's just going to stay how it is. Okay, so now we have our complete ionic. That's our complete ionic. Now, in order to give us our net ionic, we have to first cross out all of the spectator ions. So the ones that stay the same are actually this potassium. You can see that it's 2K plus aqueous, 2K plus aqueous. And the same thing with this nitrate, 2NO3 minus aqueous, 2NO3 minus aqueous. So what you end up getting as your net ionic, so this is our net, and our spectators were, so I'm going to write out right here, our spectators were our plus K plus, and also our NO3 minus aqueous. So those are our spectators. And then we get to give us Ag2SO4. So that's how you write out a complete ionic, and then identify your spectators, and then you get your net ionic.